Okay, so we talked about data structures before a little while ago. So we have stacks, we have queues, we have linked lists. Can anyone tell me what a stack is?
So an item, you can place things, and then you can just take the top one off.
Right.
First in, last out.
Yep. Yeah. So what might be a use case for a stack?
Tower of Hanoi.
Tower of Hanoi. Okay. Yeah. Yeah. We haven't talked about the Tower of Hanoi, a classic, recursion computer science problem. But yeah, you can use a stack. What about a queue? So what are the features of a queue?
It will maintain the order that they go in, so you can take them out in that order.
Right. Yeah. So you put something in, at the back of the queue, and when you take stuff out, you take it out from the front of the queue. And a use case for this, it could be something like you could have a messaging system or a job scheduler or something. So you have a server, it's getting a whole bunch of requests. It might go into a queue first in case the server gets overwhelmed, right? Can't process all the requests in real time. You can kind of create a queue, and then as processing time becomes available, it can take things from the queue and process. So it'll happen in order. We're going to talk now about, and then linked lists. So how does a linked list work?
Every item has a piece of data and then a link to another item. So you can store, so it doesn't have to all be stored together. It can be stored in separate places in memory.
Okay. So can we talk a little, Patrick, can you tell me what an item is? Is there another more specific term?
In a linked list?
Yeah. Yeah.
I don't know. I just think of nodes when I think of linked list.
Right. Yeah. So a node. So obviously. So node is the typical term used. So what are the features of a node?
A node is going to have either a parent or a child potentially, or leaf or branch. Kind of depends on the terms.
Okay, so yeah, so there could be nodes could have different different requirements depending on what kind of structure they're being used in. But for a linked list, do nodes have parents? Do nodes know about their parents in a linked list?
No, they only know the next one, if there is one.
Yeah. So a node in a linked list will have basically two things. It will have its own value. It'll have a value or some kind of data or whatever, and then it will have a reference to the next node.
And one gets designated as the current head.
Yeah. So there's different ways of implementing a linked list. You could just have a node, and then kind of have the linked list structure be implicit, or you could create another kind of linked list class that would operate on nodes. And in that case, yeah, you would have like a head node or a base node. So what's the big O for finding an element in a linked list?
And
Yeah. So can you talk about what that means?
it means it has to go through every element basically to find define the element, because it has to look for the children, and then it has to go to each child, and then it has to look for the children of that child, and then it keeps on going down the line until it finds the element.
Okay. So if I have a linked list with 100 nodes in it, and I want to find a given node, then worst case scenario, how many search operations do I have to do?
If it's the last one in, and then you'd have to do 100.
Yeah. So that's basically what n means the number of elements that you have. So if you have a linked list with 100 nodes and you want to search for a specific node, the worst case would be that the number of operations you have to do is the same as the number of elements that you have. So that's O of n. What about adding a new node? What's the big O notation for that?
It's 1, right?
Yeah. Yeah. So that would be O. I mean, you could insert it at the end or something like that. But yeah, if you insert if you insert, as you should, at the beginning, then you always have an immediate reference to the head node, right? So all you're doing is when you insert a new node, all you need to know is where that first thing is. So it's a constant time. So it's always the same. It doesn't matter if you have 1 million nodes in your linked list or 3. It's gonna do the same number of operations every time. So that's O of 1. It's constant time. Okay. So let's look at hash tables. So in Python, we have dictionary. I mean, in lots of languages, we have dictionaries or objects or hash maps called different things depending on what language you're working in. So in Python, how does a dictionary work? Let's just talk about that in general. Jared, can you tell me about dictionaries in Python?
So they have they're stored as key value pairs.
Yeah. You have some kind of thing, some kind of container, and then any slot in that container has a key and a value. So if I want to look up a specific key, what's the big O notation? Do you happen to know?
I think it's N.
You think it's n? Okay, so let's say if I have an array, or list, so
Because it's unordered. So you have to look through every item.
okay, so if I have a list and I want to look for a particular thing, let's say I want to search for 7. Let's say this is an unordered list. So this is an unordered list, and I want to search. So the kind of simplest thing to do would be to do a linear search, where I start at the beginning and I just check. I go, is this what I'm looking for? 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 And that could potentially take, so if the item is either not there or is the last one, that will take me as many operations as I have in the list. Now, if we have a dictionary, And I want to do what's the complexity, what's the time complexity for this lookup? Any guesses?
I'm not sure if it's n or not, but it's just you find it because you know it's the second entry. It's 1, whatever that is in your crazy big O notation.
Okay, so you think so? If I had 1 million key value pairs in this dictionary, and I wanted to search for a particular one, it would take the same amount of time.
Yeah, I believe so. How Python works below. I think it's indexed or something to that effect.
Okay. Any other hypotheses?
I'm guessing that it would find second right away as the first thing. Like it can, like Python can look up and find that key without going through everything.
Right. Yeah. So yeah. So that's what Jeff. So yes. In fact, that is so. Jeff and Jess are right. So we have this is actually O of 1 lookup. So it's constant time lookup. So it doesn't matter how many things I have in this dictionary. I can grab any given item by its key and find it, immediately, or in it doesn't matter. It's not tied to how many items I have in this dictionary. So that's one benefit of using a dictionary. So there are obviously trade-offs. So let's go ahead and implement something like a dictionary in Python. So a generic term for dictionary is something like Hashmap. That's probably the most generic generic name. So what is a hash?
A scrambled set of data.
Yeah. I mean, you could definitely think of it as a scrambled set of data. Would anyone else like to add to that?
It's an outputted value of an algorithm where you can feed it either a file or a string or a value, and it runs the algorithm and outputs a unique string of characters that's going to be unique to the input every time.
Okay, yeah. So I can a hash algorithm or a hash function would be something that takes some kind of input and does some stuff with it, and then outputs something else. So it could be so would the output be random? So if I gave it the same key, would I get the same output every time, or
Yes.
would the output change?
You get the same output every time. It's just supposed to be unique unless there's a collision.
Right. So we're not. So that is a good point. We'll talk about collisions in a sec, but we're not quite to collisions yet. We're just talking about the hash algorithm itself. So yeah, hash algorithm should be what's called deterministic. So if I have a function, so I'll just do whatever. So this is a very stupid hash function. So is this function pure or impure?
It's pure, right? Because it's not using anything outside of the function besides what's being passed in.
Yeah. So as long as whatever I'm passing in is not a global variable or anything. So this should be pure. So a hash function should be pure, and it should be deterministic. So the same input should give me the same output, so it shouldn't be random. And it should be, so another term that we've heard before from functional programming is referential transparency, which is basically the same thing as deterministic. So it just means every time I give it, if I pass in, you know, doesn't matter how many times I call this with the same input, I'm always going to get the same output every single time. So that's what we want from a hash function. Now, this is obviously a very bad hash function. And one reason it's bad is that I can derive the original, right? So if I get the output, let's copy this. And then I call it with, it's fairly trivial to derive what the original input is. So I can work from the output back to the original input. So in general, you don't, I mean, if we're talking about, you know, something that's used for security, you definitely don't want to be able to do that. Okay. Right. So that's the basic idea of a hashing function. It will take some kind of input and it will consistently produce the same output, but that output will be somehow different than the original output, and maybe even ideally not backwards compatible and not reverse engineerable. So Python has a built-in hash function. So I could do something like let's do this, get this thing, some big apparently negative number, and if I can do the same thing, another, I'll just change one letter, remove one letter, and we get what? What, that is giving me different numbers. Okay, I think hash is it probably takes a seed here. So if I were to give it a seed, then it'll be fine. So we'll ignore that for now. Actually, let me try to use another seed import. To encode this. Put it here. So the particulars don't really matter. I'm going to do it like hex digest. Okay. So yeah, sorry about that. So this doesn't especially matter, but if I do it, this should give me the same thing every time. Okay. So I'm sure I can double check the documentation, but I'm sure this takes a seed that you could control and make it consistent. So if I just change one feature here, notice that I get a totally different hash, even though there's only one letter difference in my initial input, the output is completely different. It's not like they just changed one character in the output or something, right? So it's very difficult to go from, to find a pattern here. All right. Okay, so that's basically the hash part of this. So the way a hash table or a hash map or a dictionary works is that you have some kind of container structure, and we'll just use an array. And what we want to make sure we can do is have constant time lookup. So we want O of 1 lookup. So if we just have an array and we store a bunch of items in the array, we're not going to get that, right? Because if we want to search for a particular item, we're going to have to look through every single item to look it up. But if we can somehow make that index correspond to what our item is, then if we have that name that we supplied or the key, then that key will be instantly convertible into an index. And once we have that index, we can immediately look up what we want. So we're not gonna have to search through every single item in the array. We can just immediately go there. So I'm gonna create a class called Hashmap. Itself, and my hash map is going to need some kind of container, so I'll do self.container, and for now we'll create an empty array. So this is enough to get us started. But let's talk about the features that we're going to need for a hash map. So we're going to keep it very simple, and what we want our hash map to be able to do is to insert a new item. So I can, add a new item, or I can retrieve an item. So we'll have these two methods implemented. So we'll do def add. Okay, so let's talk about how we could convert a string. So we'll just use strings for keys. So how can we convert a string into an integer?
We could do something with the ASCII values of the letters or characters.
Okay, cool. Yeah, we can do that. So def, I'm gonna call this a hasher. We'll take a string. All right, so we could yeah. So how would you like to start that off? So we get the ASCII value. How can we get the ASCII value for a character?
I need to look up that method. I know to go from a value to a character, I think it's char, but I'll have to look up what it is to go from.
I think it's ord.
That's right.
So if we want, can you talk me through what you'd want this hasher function to do? So if we can get, so we know we can use ord to get the ASCII value for every character.
Will ORD work for multiple like if we put the whole string into the ORD method, will it do it all, or do we need to separate it into characters, like a list comprehension?
Yeah, I think we're gonna need to separate it.
So I would do a list comprehension to make basically a copy of the string, but separate it out by character.
Okay.
So with the bracket, or I guess you need a variable to hold it first. So we'll call it string array.
Okay.
Equals, and then the square bracket. So char for char in S. That might do it. I'd check and see if that would work first.
All right. So we'll call this okay. So we have
I can't see the bottom of.
oh, sorry.
There we go. Okay, yeah. So now we can do, I guess we could do a second, forgot what it was called on line 5, or we could do it within that. Yep.
Yeah, we could probably do it here. So
Yep.
Print this out.
There we go.
Okay,
And
so
then-
now we have a bunch of numbers.
So then you could do anything, if we're just trying to get it into one large integer, you could sum those, or you could do them one after the next, but I think it'd be easier just to sum them.
Let's try summing this.
There you go.
Okay, we've got 532. So now we, let's say we get passed in a key, which is hello. So, it's like we want to make a dictionary. Something like that. And then we do my dict hello equals whatever. Something we want to pass in. So that's kind of what we're trying to do here. So this is going to get turned into a number. So now we need an array that has, I guess, at least 532 slots in it. Seems like a lot. And also, I mean, what if our key was, a much longer string? So we're not going to really, we won't necessarily know how big this container has to be. So what if we wanted to restrict this hasher to only output numbers between 1 and 10?
We could divide that ASCII character by some value to get it smaller.
Okay.
Or mod 10
Okay.
plus 1.
We do mod 10 plus 1. That'll never give us 0. We can do it. Let's try this. Okay, so that's manageable now. Now if let me just try a bunch of these. Something like that. 2, 1, 3, 5, 4. Nine. Wow, I'm not getting any. Wow. What good luck I'm having. There we go. It took a while, but eventually it looks like our hasher for ATL and the hasher for Haya there both give us 3 as an output. So we've solved one problem. So now we know that our hasher function is only going to give us a value between 0 and 10, right? Or 0 and 9. So we can fix the length of this. So we solved the problem of how big does our container have to be. But in solving that problem, we created another problem. So Jeff mentioned collisions earlier, and that's basically what we're dealing with. So if you have a hashing function and you have a finite number of potential values and your container is a finite size, depending on how your hashing algorithm works, you're probably at some point, if you have enough, given enough time, you're going to have something called a collision. And you can decrease the chances of that happening by having a very, very large container. So instead of 10, if we made this like 5 million, and typically dictionaries only have a few entries, then chances are low that we're going to end up with collisions, but you wouldn't want to implement that in a program that people depended on. So we have this hash function, and now we've basically limited what values it can return, but we've created another problem where now we don't necessarily have unique slots. So that's called a collision. There are a few ways to handle that. We're not going to get into that just because it will take a little bit more time, but we're going to focus on the basic use case. So we're going to be a little bit lazy and just say, so we want to create a container, and so we'll do something like none. Well, we'll still do 10 for now, but we could make this any number. We could even pass it in here when we initialize it. Let's do that. Okay, so now we have a hash map. Let's create an instance of the hash map. Just look at the container. We have this basically, an array with a fixed number of slots that just has none for everything. All right, so let's say I want to, let's say I want to add, I want to add an item to this container. So what are we going to need to pass to add item? If we want to add key value pairs.
If we're adding key value pairs, doesn't container need to be a dictionary?
Well, we're making a dictionary.
Oh, okay.
We'd want to pass the value, right? Then we would derive the key using the hasher function.
Okay, so we could, so there are a few ways we could do this. If we want to have a key and a value, or if we just want to have, let's say, a value and we use that as a key. So we could potentially do either one, but let's try to keep it structurally more like a dictionary. That'll allow us to have, we'll enforce strings for keys, and then the value could be anything. So we'll do pass in a key and a value. And what we're gonna have to do here is we're gonna take the key and we're gonna have to hash the key to get a number that we can use as an index for this array. We're gonna have to bring this guy in. So I'm going to change this to key. And return this. Okay. So we have this helper method here. And are we using self in this function or in this method? So does this mean that this is going to break if you don't use self?
You need that decorator method.
Yeah, so it won't break, but if we're being, very conscientious, we can get rid of self since we're not actually using it, and tell Python that this particular method doesn't take self. We do get a static method. All right, so now we're going to somehow get this key. So we'll get the hash index, and we'll call hasher. So let's just try running that. Print this for now. Value, so. Okay, so now we call the add item function. We get a hashed index based on the key. So if the key is hello, we're going to get the hashed index of 2, which is nice because it's within the range of the our container. So what's the next step?
So Chad, I'm a little bit confused about what the containers for. Are we putting each, like a key value of the, like the original value and the hashed value as a dictionary into the container at that slot? Is that what's happening?
So this, what we're making is basically a dictionary.
The whole thing, not just the container.
Yeah, so we're not gonna, so we can't use a dictionary within it. It's like defining a word by using the word. So we can't use a dictionary. So we're gonna use an array. And the array, we're creating a fixed length array. And we could have, 10 or 100 or 1,000 or 1,000,000 or whatever. And what we're doing is we want to convert keys into indices. So once we have, so we convert this key into an index using our hasher method. And that gives us something, an index. So now we can use that in our container. So if we want to add 3, so we want to store 3 in this container. And we want to access it using this key, hello. So hello, when hashed, gives us 2, which is right here in our container. So then we would add 3 here. And then if we were to look this up in the future, we can use the same key, which will get converted to this index, and then we can immediately grab it here. So that gives us O of 1 constant time retrieval or search.
I think I understand now. So you're using the index in place of like a key, and that gives us O of n or O of 1, even though it's a list. You can go directly to the index, just like you can in a dictionary.
Exactly.
Thank you.
I think, don't we want to, under add item, we want to say like self.container bracket hashed index equals value?
Yeah. So we're gonna want to insert. So we could do it so something like hash, let's do self dot insert. There's a built-in method to do this. So we'll take the index and we'll take the thing you want to put there, which will be value. And now if we run this and print our container again. I'm gonna use the debugger here. I'm gonna do it pro style. Okay, so let's print the H. Can you guys see this here at the bottom? Okay, so I have H, so H dot. See my container. So I've stopped here, so line 40 hasn't actually executed yet. So let's do H dot add item. And let's print out the container again. You can see that it's actually been inserted here. Let's try another example. Let's start inserting something else. Check out our container. So that last thing we can actually see up here as well. I'm going to add a watch because I want to check out what the container is. So okay, so I can see that whatever Apple, the key Apple, when run through our hasher function, returns 0. So the 0th index, this gets inserted there. and hello becomes 2, so it gets inserted in the 3rd position, and so on. Or it must be 3. So are there questions about this so far?
Why does it have a length of 12?
That is a good question.
Maybe it's because of the insert. It's actually inserting and making it bigger.
It must be. So let's try. Okay. I guess insert is actually creating this thing. So yeah, good catch. So we'll just do it this way. Okay, so now we have the ability to take in a key and a value, and then hash that key and store it in the value, or store it in the container. All right, what about getting an item? So now that we've got some stuff stored in here, how are we going to retrieve? So I want to grab the value for hello.
In that case, we'll need the key again to be passed in.
Okay.
Run it through the hasher, and then look up and get the hashed index again, and then look up the or print or something the value of that index.
Okay. All right, so let's try doing that. So you can see, and let's add another one. Okay, we have 2, and now if we want to get something, so get item. And is the value that we want to get there. So what's the time complexity here for the lookup?
Is it 01?
Yeah. Yeah. So because we've used the hash, we now, even though our container is an array, we're adding another step here to make lookups of 1 instead of of n. So that's basically it. So there are collisions, and there are a couple strategies for dealing with that, but we're not going to talk about that. It's not that much more complicated, but
And collisions would just be if you put 2 in the same index, like if 2 ended up with the same.
Yeah. So if 2 strings hash to the same, return the same value from the hash function, that means that we're going to end up either replacing, if we didn't handle it, we would just replace probably what was already in the container. So I mean, that would be a problem. So I'll just say that there are two basic strategies for dealing with that. One is you kind of keep everything the way it is, but if the spot is already occupied, then you just like try the next index over. You just try another index. So you add one and then try that or something like that. So there's a little bit of extra work. Another so that's one. What's the other one? Yeah, the other one is basically you just make. So you would have each one of these, instead of being none, you would have it be like an array or something, and then you would append. Yeah, and it makes it slightly more complicated because once you have the index, you also need to then look up the key. So there's a shorter lookup there, but you can basically reduce the time that takes by one, having a larger. You can have a larger initial container, so collisions will happen less frequently. So at a statistical level, it won't affect the time complexity.
So I'm feeling kind of stupid. I'm not sure I understand the time complexity thing. What is O of n, O of 1, that kind of thing?
Yeah, so yeah, don't feel stupid. Again, we still haven't officially talked about this, but so the idea is we'll talk real quick about this. So let's go this. I'm gonna build this out. And so if I want to find a particular value in this list, so we've done linear search, right? So let's just implement linear search real quick. So so we give it a list to look through and a target that we want to find. So we can do something like for yeah. All right, so let's search. I'll give it my list, and let's look for 12. So time complexity is usually determined by worst case scenarios. So if we run this, we can see that it's not found, right? So the question is, how many operations happened inside this function?
Six.
Huh?
6.
Yeah. So 1, 2, 3, 4, 5, 6. So we had to loop over 6 different things, and every time we do it, we do a little check, right? And if we had 100 items in this list, how many operations would we have to do, assuming that this wasn't in the list?
100.
Yeah. So that's called O of n. So n is a stand-in for basically whatever you're giving as input. So as this grows, as our input grows, the number of operations we have to do in the worst case scenario grows correspondingly. So if we have 10 items in our list, we have to do 10 operations in the worst case scenario. If we have 1,000 items in our list, we have to do 1,000 operations in the worst case scenario. Does that make more sense?
So O of 1 means that you only have to do one operation to get your solution.
Yeah, it means it's the same. So let's do another list. Instead of doing linear search, I'm just going to grab the I'm going to grab the second index of my list. So how many operations do I have to do in order to get this value? I mean, we don't see what's happening because it's implemented in Python, but it's basically the same. So it's going to go, what's the memory address of my list? And it's going to add, 2 or whatever, 2 units to that. And then it's going to immediately jump here and give that to you. So if I have 1,000,000 items in my list now, and I want to get the thing in the second index, I want to get the thing in index 2, how many operations do I have to do?
Just
Well,
one.
Yeah, so the answer is it doesn't change, right? It's the same whether I have 6 items or 10 items or 100 items or 1,000,000 items. This operation, the same number of operations happens regardless. So this is basically independent of the size of my input. So it's O of 1. So this is always going to be a constant operation. So we'll talk in more detail about big O notation, but this is basically it. This is like 90% of what.
Can I just ask a big O technicality? So if there's 6 items in my list, so that would be a potential big O of 6.
For linear search.
For a linear search, right? And the item was the second item. Does big O tell us the potential number of operations it could do, or does it tell us the number of operations it actually will do?
Yeah, so it's a way. So big O is used to abstract away from the particular machine architecture. So if we just use something like time, right? So how long does it take to run this operation? Well, we could measure that, and then we could write another algorithm, and we could say, oh, it runs faster, so it must be better, right? But there's so much variation, depending on maybe the implementation of Python or what machine you're running on or what other processes are running. So, timing something is not really a reliable metric. I mean, it is and it isn't. So, the smart people who do computer science stuff come up with a way to kind of abstract away from the particular implementation and talk about the overall structure of the algorithm. So the overall structure of the algorithm, this is an O of N algorithm. Because yes, it's true that if I always search for the first thing, it's going to be essentially immediate, right? But that's kind of an implementation detail. So what matters is that, potentially, and Big O is especially concerned with worst case scenarios, right? So what is the worst case scenario here? Well, the worst case scenario is that it doesn't exist in the list. So it has to traverse over every single one. So you don't necessarily, when talking about big O, you don't worry about like average use case necessarily, or you almost always talk about the worst case scenario. Are there any more questions about that?
Is there anything besides O of n and O of 1?
Yes, yeah, there's a whole bunch, but the main ones that we focus on, basically O of n, O of 1, O of n, and O of n squared. We'll talk more about these, but there are a lot of intermediate ones. All right, I'll stop sharing.